Live, and what I'm going to do is I'm going to try and spotlight you, Shane,
Oh, okay.
and I think I'm going to see if I could spotlight myself too. And then, oh, that didn't work. All right. Well, let me just pin instead. All right. So let me cancel, and I'm going to cancel your spotlight. Where did I
All
go?
right.
I'm so glad this is on the live stream, right? All right. Well, let's just go ahead and get this rolling with you. So Shane is a professor at University of Virginia, um, and he's doing astrophysics, black holes. Shane and I met in grad school, and he had to put up with me back then. I was just as obnoxious then.
More.
It's hard to believe. That's true. But so, Shane, maybe you could just tell him a brief little bit about your background. Oh, and Jing just got in here too. Let me see if I can change this to gallery view. I'm going to try and pin you guys instead of spotlight. So pin, and let me see if I can pin Jing too. There's Jing. Let me see if I can pin you too. Oh, well, I'm not sure. All right. So maybe I might just have to manually go between you guys. Sorry, I'm not adept at this Zoom going back and forth with multiple people. So, like I was saying, Shane is professor at University of Virginia. Jing, I don't know if you can see her there. She's a professor at UC Merced. They both went to grad school with me, and so maybe we'll just start. Actually, Shane, do you mind if Jing starts? Because she said she's got to take off at 5:35. Is that cool?
Yeah, that's fine.
Just in case we get rolling. So Jing, go ahead and start. I'm going to put you on the speaker view. And by the way, Jing, we are live streaming. Hopefully that's okay with you. So some of my students watch on YouTube. All right. And just giving you a heads up. So maybe you want to mention just a little bit about your career arc briefly, or anything that you feel like saying, or like how you ended up at UC Merced, or anything like that.
Oh, that's
or whatever you feel like talking about.
Yeah. Let's see. So the career arc starting from college.
So maybe after grad school or
after grad school. Okay, yeah. So let's see. I never knew if I wanted to go to grad school. In fact, I was pretty certain that I wasn't going to go to grad school. I thought that 5 years is a very long time. That's a lot of my life. But then, so after college, I went into at the time, as in vogue. At the time, everyone was going to financial institutes. So I joined one in LA, and then about immediately decided that was not for me. and then I said, okay, what do I do? So after 2 months, I quit, and then it was a turning point. It was probably in my so after college, I was fairly burned out. I thought that this needed a change, and then after I quit my job, I was the turning point was me looking at unemployment form, to which my partner at the time said, well, you probably should fill it out just for security. But I thought that, let me go look for a job in the lab. So which I have which I was working throughout my undergraduate life. And then I went to my TA at the time, so it's good to know form a network of the teachers and that you have and the teaching assistants that you have. I went to my TA who was in high energy physics, so my undergraduate degree was in physics, and said, "Do you have a job?" And so they say, "Oh, sure," and I started working in a lab that of my undergraduate institution that was looking for high energy particles from far away, and then we built these plastic what's called scintillators that measures high energy particles, and then as it enters the plastic, it sort of slows down and it traces the particle trajectory. So those are detectors. And so I worked on that, and then just gradually got more and more into it, because I guess it's because the lack of, because I didn't have to work on classwork, so I could focus entirely on whatever it is I was doing, and I got excited about it. And then a year later, when in November, Thanksgiving, I remember getting up and going to lab and thinking, oh, hey, if I'm going to do this on a Thanksgiving, I probably should go to grad school. And then the part of the motivation for going to grad school was also because my parents are, they're both are chemists, but they never had for whatever reason, they had never had the opportunity to go to grad school. And they're way smarter than I am. So I'm like, well, maybe I should get one just so that on their part.
I got
you. And then went to grad school, met Rob. I remember the first time I met him, he showed up and said, oh, you have to listen to this CD. And then he played it. It was a MATLAB CD. Let's see. So in grad school, I was pretty sure I wasn't going to be academia because academia is hard. But during my last year in grad school, there was another downturn in economy, and my ideal job, which is in national lab, so in this particular lab that I was just focusing on, they had a hiring freeze. So I said, okay, maybe I'll go to postdoc. And then when I was looking for postdoc was when my sort of research world really took on a different dimension. I've been trained in building machines and trained in physics, but I failed biology in high school and I never took any biology. But during the time I was looking for postdoc, I realized that a lot of physicists are applying state-of-the-art scientific instruments to answer important questions in biology and sort of rewrite the textbook of biology. And that got me really interested in it and sort of redirected me down this road of being in the research institute. So yeah, so I study how to control trafficking cells and for cellular health and human health.
How long have you been at UC Merced now as the faculty member? Is it like 5 years, 10 years, something?
Since 2011, November 2011. Okay. So it's going to be 9 years. Yeah.
Okay. Do you care if I skip over to Shane and let him kind of tell his story? Okay. Yes. So Shane, whatever you think.
Well, so I went to graduate school in physics. I did my undergraduate degree in physics. And so I'm from North Dakota, which is a really cold, snowy place. You might meet someone from an even worse, colder place at some point on this. But and I went to undergrad in Pittsburgh at Carnegie Mellon because that was the farthest away I could get from home, given my options. And then that wasn't that much better in many respects. So then I went to Santa Barbara because Santa Barbara has these nice pictures of the beach. And it's a pretty good place to do graduate school. So, and I met Rob and Jing there. And so I had a lot of fun for 6 years. I stayed for 6 years because why would you leave Santa Barbara after only 5? And grad school is tough, but it's really fun. And even though you don't have a lot of money compared to your friends who go off and get real jobs, you have a lot of free time and you get to do a lot of things. So that was cool. And then after grad school, I knew I wanted to do astrophysics. I started studying black holes, stuff falling into black holes. Well, in graduate school, I was a sort of theorist. So I did like computer calculations and solved equations and stuff. And I basically got my very first choice dream job for a postdoctoral research right out of grad school. I got really lucky, insanely lucky actually. And so I got this job in Princeton at a place called the Institute for Advanced Study, which is where Einstein was when he was, after he moved to the United States. And so it's this really awesome place to do research. And so I got to spend 4 years there. That was really cool. And then in my field, it's fairly common to do more than one of these 3 to 4 year stints of postdoc. So then I moved to Toronto to this place called the Canadian Institute for Theoretical Astrophysics, which is also a really good place to be. And Toronto is a fun city. And then at the end of 4 years there, I got a job as an astronomy professor in Virginia. So just to count that up for you, that's 6 years in grad school, 4 years in Princeton as a postdoc, 4 years in CETA. So after 14 years, people decided that I was maybe good enough to be hired for a assistant professor position. And so I've been at here for 6 years. I just got tenure. So I've had my,
Yeah.
but that means I basically was in astronomy for 20 years without any permanent position. So that's the
After
downside.
bachelor's.
After my bachelor's, yeah. So
Oof.
so that's some of the downside of being an academic. I had to move 3 times. I was in places I liked, but you know, but I was doing the whole time. I was doing research that I really loved. So, you know, it was pretty fun. And I get to study all sorts of stuff out in space. My favorite thing is black holes because those are, I think, just really interesting. But
can you tell us a little bit about that Nobel Prize black hole stuff really quick?
Sure. How quick do you want me to go?
Moderately quick, because I was hoping to get back to Jing before she has to leave.
Okay, sure. Or should she go first?
No, go for it.
Yeah,
No.
just a brief.
Okay.
Yeah.
Okay, so so I know I've met everyone who won the Nobel Prize, although I don't know any this year, but I don't know any of them well. So they gave the prize to three people. They usually give the physics Nobel to 3 people, and it was all black hole related, which is kind of surprising to me because normally they only give you the Nobel Prize when like the research is really solid and everything's proven. And black holes, I think, are still kind of in the area, a little bit in the area of, well, we think they're black holes, but we're not really sure. And so the theorist was this guy, Sir Roger Penrose, this British guy. And, you know, he worked a lot on the 60s. He did all this really cool math. He basically got the Nobel Prize, though, because Stephen Hawking is dead. If Stephen Hawking was still alive, they would have almost certainly given it to Stephen Hawking instead of Penrose. But sometimes you get points for just living longer than everyone else. But so he did a lot of cool stuff like Stephen Hawking to study the theory of black holes. And he's a very smart guy. I'm not trying to take anything away from him. He's way smarter than me. Although he's got a little kooky in his old age, but that's what people tend to do. And then the thing I know more about is the other 2 people they gave the Nobel Prize to. One was a professor at UCLA named Andrea Ghez, and the other is a professor who's actually part-time at Berkeley, but he's also he's German. His name's Reinhard Genzel, and he spends most of his time in Germany. And they basically got the Nobel Prize for studying the stars in the galactic center and showing that they seem to be orbiting around a really compact supermassive object. So they can show so basically if you trace the orbit of a star, have you guys done Kepler's law yet in your class?
Yeah, they coded that up last semester, I think.
Yeah, okay. So you basically, if you see the star's orbit, you can see it making a nice ellipse. You can just apply Kepler's law and get the mass of the object inside. And you can show that that object has to be 4 million solar masses, okay? Oof. And it's in a very, very small amount of, 4 million isn't that big of an object compared to, say, the whole galaxy, but it's because the orbit is a very small radius, right? In terms of the size of the galaxy, it's a huge amount of mass in a very small area, and it emits very little light. So it's pretty much impossible to imagine anything else that it could be other than a black hole, right? So it's the strongest, in some ways, I think the strongest evidence for black holes, which is why they won the Nobel Prize. But the question, I'll just say this real quick. So why did they do it and not someone else, right? Why, if you're just looking at stars, what's so hard about that? And the thing is, one thing is you have to monitor, these orbits are like 10 to 15 years. So you have to monitor it for like 30 years to see, the orbits go around a couple times. But the really cool, the really hard thing to do here is that you have to like peer through all this dust. So you have to build your telescopes to look in the infrared. So you have to build them way up on mountains because some of the infrared gets absorbed by the atmosphere. But the thing is, these orbits are really small and they're very far away. So the resolution you need to measure these orbits is much smaller than about an arc second. It's like hundreds of arc seconds, or maybe hundreds of milliarc seconds or tens of milliarc seconds, which is just a very, very small angle. You don't really need to know. But the thing that you do need to know is it's much smaller. So when you look at any star in the sky, because we're looking through the atmosphere, the star gets moved, the spot of the star gets moved around. That's what we see when we see stars twinkle. It's just the atmospheric turbulence moving the position of the star, because as the light goes through the atmosphere, it gets refracted with these little turbulent cells. And so that basically spreads the star out. And so even though the telescope, we have these 10-meter telescopes that have the power to resolve sizes smaller than like this arc second or half an arc second, the atmosphere smears it out. And so you have to do way smaller than that. So you would think it's hopeless, right, to even do these calculations because the atmosphere is the limitation. But what they did was they invented this method called adaptive optics, where they basically, if there's a bright star, if there's a bright star, you can look at the star, and then by watching that bright point move around, you can measure the turbulence in the atmosphere, and it varies on millisecond timescales. And then you have a deformable mirror that you can change its shape on millisecond timescales to correct for the atmosphere, and then you can get resolution that's actually smaller than that what you'd get with the atmosphere. But then that's the problem is there's no bright star for Sagittarius A star. So they actually have to shine lasers up into the sky that reflect back on that turbulent layer. And they actually measure that layer using the lasers to measure the turbulence, and then measure these stars and their orbits. So it's just this incredible engineering feat, and just all this work over decades by many people. So it's really impressive, actually. I mean, I think it's a really well-deserved prize.
Cool. So a quick message to my students. Students, you can go ahead and keep piling up the questions in the chat. So we'll get to those in order. So if you have questions at any time, throw them in the chat. But I wanted to get back to Jing one more time before she's got to get out of here. And then Shane, did you have a couple extra minutes, or you got to get going?
Yeah, I'm not in any big hurry.
Okay, I really appreciate it. All right, so Jing, let me see if I can get you back on the screen there. There we are. So Jing, I think I would be remiss if I didn't have you at least mention something about what it's like for you being a woman in science and your experiences or your advice to females in the class here. I don't know, just any topics you have on gender in the sciences in general. Is there anything that jumps out at you as something you want to say relating to your experiences or what daily life is like? Is it horrible? Is it good? Or is it getting better? Is it getting worse? That kind of thing.
I think science, among all the fields that I can think of course, I only have real experience in science. I think in science, among the different fields, in my personal opinion, is perhaps the one of the more progressive field to be in. That is to say, it doesn't really matter if one is junior or senior, quote unquote, expertise is not tied into one's position by one's experience in the field, but not one's position in the field. Does that make sense? So I've never met a scientist who's worth who's a really great one that have any of the concerns that one might have. That is to say, that is a good readout. Science is a human endeavor. You're going to meet all sorts of people, and one of my professors in undergrad said that at Caltech said that he loves to be a scientist because he can be a child his entire life, and because he get to pursue things that are just out of fundamental curiosity and ask curiosity-based questions and test hypotheses and so on. But the downside is that you do get to work with people who are kids your entire life.
With the childlike mentality. Yeah.
But in terms of research-wise, I've never had anything that had to deal with hurdles that one might associate with gender and so on. That being said, there are it's a human endeavor. There are, I think there is challenges for everyone involved in the field. If I look at focusing on women, because I am one, if I look at a different generation of women, there are different approaches. That is to say, that I can point to and say things are getting easier for us. That is to say, the various generations, earlier generations, my professors, the few who are women, they have to really be in the, my observation is that they have to be particularly tough and taking on the sort of male perspective of approaching problems and approaching handling things. But then over time, there is more of a gentle transition that I think people are more allowed to be more diverse in their interaction approaches and so on.
Gotcha.
I will just conclude that by saying that if you ever run into, regardless of which group you're in, if you ever run into problems that say as a woman that you feel disqualified because of you're a woman, then you call bullshit on that. A good role model is to look up this the sentence: strong verbs, short sentences. It's a famous quote by what's her name?
You said strong verbs, short sentences.
Short sentence. It's a famous quote by Bernadine Healy, Bernadin Healy. So she pioneered the I think vaccine trial or medical studies that includes both female and male instead of just male. So
okay, cool. So Jing, I know you said you had to get going at 5:35.
Oh, wait until 5:40. So
okay, cool. Well, how about yeah, so let's go ahead and get into some questions here. I saw one of them said, do you have to go to grad school to teach science or math? I'll let you field that one, Jing.
Depends on which level of math or science. So at Santa Barbara, there was credentials that you can take in terms of teaching, because teaching is a different beast than doing the math and science. There are different types of schools. So my student one really looks up to Rob's position. He wants to make an impact in the society. He wants to teach at a junior college, and Rob's position is exactly what he wants. And I would say that that's actually a very tough job because of various reasons. Rob will tell you exactly whether or not you need to go to grad school to teach science or math.
Yeah.
Well, I taught high school for 1 year when I was in grad school, and the science teacher that I was teaching with, one of them graduated from Caltech with a BS. So they don't need to go to grad school, but you get a higher pay if you have a master's or PhD.
Right. Okay. And then just to keep it cruising along here, how is your teaching at the university compared? So I'm looking at Tom's item in the chat. He says, how is teaching compared to your expectations before you started? What did you expect and what's the best? I guess of being a university professor, so university professors, just so you know, everybody, it's mainly research and a little bit of teaching. I think is that a safe way to say that, Jing and Shane?
Yeah. I teach one class per semester. What about you, Shane?
I teach one class per semester. So when I'm evaluated, it's assumed, it isn't always true, but it's assumed that I spend 30% of my time on teaching.
Got it. So in regards to that, is there anything that you encountered that you expected, or what's the best part of your job right now?
Teaching for me, the best part is to actually interact with my students. So when when I first started teaching, it was very, very hard because it was hard to gauge where my students are. Because you have to remember, by the time that we get to teach, so Shane told you his academic career. It's been 21. So the amount of time lapsed since I took the class I was teaching to now, is almost legal to drink alcohol. So the perspective. So when I first started teaching, the perspective of the student was completely absent to me. So the most beautiful part for me is to sort of learn to view things from my students' perspective and find out what are how, because different students are also different for different classes, find out how to perhaps to the degree possible customize it and to lead them through the hurdles, rather than, because it's the hurdles that the perceived difficulties that keeps most people from going forward, not actually the material itself. So that's the challenging part. But it's also just really neat to be able to solve some part of it. You want to sort of like hold the expectations, but not be so, but in a friendly way.
Okay. Should I get Shane's? Okay, I'll get Shane's, and then hopefully, Jing, if you have time, I'd like to pick your brain for one more question after that before you go. So Shane, how about for you? I don't know if you remember the question. It was, how does teaching compare to your expectations, and what's the best part, or is there anything you didn't expect?
Teaching specifically? Actually, I like teaching way better than I thought I would. So to be honest, you know, I always kind of expected to have to teach as sort of like something that I would be expected to do. But, you know, it wasn't that I was like, I thought teaching would be awful. It's that I thought it would be okay, right? And that I would do it, and then I would spend all my time doing the research, or as much time on research. But then I started teaching, and I actually really like it. I mean, I like interacting with students. I like answering questions. I like discussing things. One of the things I got to do when I got here was they asked me to make my own class, right? So, and so I made a class on black holes that anyone can take, right? So it's for non-science majors. And so it's one of the, you know, it's become one of the popular classes at the University of Virginia, and lots, I mean, I have 200 students, but I have like, you know, still have people on the wait list. And so it's, you know, it's a lot. So it's really fun to teach, right? And it's actually been great, you know. So I made that class in 2015. Since I made that class, we've observed the first merger of black holes with gravitational waves. We have the first image of a black hole. Somebody asked about that. We were having people winning Nobel Prizes. It's a really fun course to teach. And but I like teaching all the courses I teach. It's pretty hard. It's very time consuming. You have to be very well organized. But it's
so
fun.
That's why I'm so bad.
So Rob is an excellent teacher. I think hopefully you're all aware of that. But
not in ERT mode. Not in this online. It's tough.
Oh
man.
yeah, online is horrible. Yeah, hopefully this will never ever happen again. I hate teaching online.
Yeah. So maybe I'll get Jing one last question, then come back to you too, Shane. So Jing, so I tell my students that coding is really important, and that everybody's got to do it. And then especially if you want to get a job in physics, you have to code. I just don't even think you can get away with it anymore, right? Is this true?
Well,
in your opinion?
I don't see why you wouldn't want to have that technique under your belt. It's just like using screwdrivers. Why wouldn't you want to have it?
Yeah. How often do you use it in your daily life? Do you use Python, or do you use other languages, or?
Well, with my lab is, so I'm trained in numerical simulation and experiments, but my love is doing experiments. So my lab is primarily experiments. So during regular time, I only just resort to simulation if the reviewer asks for that component, or if that component makes my study more
robust.
Yeah. And it makes a huge impact. But now, because we're very challenges and so on, I've switched to primarily numerical simulation. And part of it is because my graduate student, it has training in numerical simulations from undergrad. So the switch was enormously easy smooth for me. And also because the undergrads in my lab are just fearless. And so even though most of them are in biology, half of them are in biology and who haven't done this before, and they'll just say, okay, yeah, let's just learn Python and then do it. Python is good because it's free. You don't have to be tied to a specific programming language. But all of it are basically just like a language that you figure out how to tell the computer to do the things that you want it to do.
Do you do a lot of MATLAB too, or no?
I do yeah. Most of the things that I work on is in MATLAB, but my grad student wants to do teach the undergrads in Python because of the accessibility, and so it's fine. So it's essentially the same language with slight syntax difference. It's like different dialect of the same Valley English versus LA English versus San Francisco English.
I gotcha. So Jing, you probably need to get going, right? So everybody, let's give Jing a cheesy Zoom round of applause here, and then we'll ask Shane a couple more questions and get him out of here. So
I saw a question.
Go ahead.
So if you want to get involved in undergraduate research, do it. The thing that I look for in a student is motivation. So if it's some sort of drive to follow up with, to push the project forward rather than treating it as a homework. That's what I mean by motivation. A good way of getting into undergraduate research is summer research fellowships that gives you. So there's I have a list of summer research applications and so on. Usually the due date is in February, and so you can have lots of time to prepare for it. It's really great. Of course, not in pandemic you can't really travel, but unlikely to be travel, but that's unlikely to have to keep on going forever. So it's a great way of getting research experience during the summer, and you get paid for it, and you get your travel and housing and so on all covered. So if it's,
hey Jing, are you able to throw like your website in the chat, so in case some of my students want to look at that instead of listen to me in the last half of lecture, they could do that?
Oh no, I do not want to divert our.
No, you should. Well, I don't know. And then who knows? Do they have? Are you taking REUs in the summer or not?
I will send you the list of
REUs. That sounds good.
And
I'll post it to them later.
It's usually in the past I've hosted various undergraduates in my lab, but right now it's really hard to do just because of books. And
understood.
But
maybe in 2 years or something. Yeah. All right, Jing. All right, we'll catch you later. I'll get back over here to Shane. Jing, I really appreciate you taking the time. All right.
Lovely to be here. Bye, Shane.
All right.
Bye.
All right, Shane. So whoops, we got Ryan on the screen. Where did Shane go? Sorry, hold on. Give me a second. Oh, I'm just trying to look for you in my list. I got to find you in this list of people. Okay. All right.
Do you want me to answer the Python computing question, or is that over?
Sure, Shane, you go ahead. Here's my deal. I always try to convince my students that it's good to learn as much coding as possible. Just because I feel like I was maybe one of the last people to get through without having to do coding. And now it's like, I feel like every physicist has to do coding, but maybe I'm wrong. Yeah.
I mean, it's definitely rare that you do nothing, right? And so, but I mean, I'm a computational astrophysicist mostly. So I spend a lot of my time coding. I use the main thing is you use whatever coding language is the best for whatever you need to do. And so if I'm going to I do simulations of stuff falling into black holes and then the light they emit. Those things use like 10 million CPU core hours, right? So these are these are like simulations where the electricity usage for doing like 2 or 3 simulations are basically the cost of, I mean, you could do several households of electricity for a year, right? So these are huge energy resources. So you want to make sure your code is as fast and as efficient as possible. So for those sorts of things, you're basically coding in C or C++, possibly with GPU applications. But then if you just want to plot something, or you want to like do some analysis on your simulation, then usually Python's the easiest thing. And of course, it's useful to teach students Python because Python is pretty widely used outside of just physics and astrophysics. So that's why it's particularly useful to use. In fact, I can show you, I was just doing a little work here. Let's see if it works. So this is my picture of a black hole, which was created using Python to plot. It's not a high resolution. I was just testing the code. But it's using Python to do the plotting, and the calculations, the tracing of the photons through the black hole spacetime, that was all done using C++.
Right on. So now that we're down to just you, Shane, let's see, students, does anybody have any more questions for him? And if not, I suppose we could give him a round of applause too. But does anybody have any other questions for Shane while he's here?
I have a question.
Go for it.
What is it? You say, basically you say like you're only teaching the one class.
Mm-hmm.
So your main focus is going to be on research. How do you manage a research project with teaching assistants? No, not teaching assistants. Research assistants, I guess.
Mm-hmm.
How do you manage that?
Yeah, kind of badly usually, but so the thing I don't, if you wanted to say what do I not like about my job, it's that it's too many jobs, right? So the teaching could easily, if I wanted it to be, could turn into a full-time job. I'm basically, I said it's 30% teaching. It's supposed to be 20% what we call service and 50% research. So the service means like all the stuff that I have to do to keep, like to support the university.
Committee work.
But also things like I have to referee papers. Like I decide whether the paper is suited for going into a journal. I have to review grant proposals. I'm doing that right now. Unfortunately, that takes up a lot of time. And then it's the 50% that's left over for research. But oftentimes the teaching and the committee work push into that. So one of the things is I rely on junior people. Right now, there's people like people who have their PhD called postdoctoral researchers. Sometimes you have those. I don't have a postdoc researcher right now, so I have 3 grad students who work with me. And that's really actually kind of hard though, because especially as a theorist, it's a lot of one-on-one interaction. So I spend a lot of time just keeping my grad students kind of going, like helping them with the problems that they face. But the main difficulty is that's then 3 different research projects that I'm managing, in addition to collaborations that I hold and my own research, which I'm doing on top of all these committee assignments, which I'm doing on top of the teaching. And so you have to get really good at organizing yourself so you can bounce between these things and be efficient. It's really, and the thing is, no matter how good you are at it, you can only do so good of a job. So that's where I feel really bad. So what you learn as a professor is what you can basically do a half-assed job on and what you can't. And so so anything you can do a half-assed job on, you do a half-assed job because you don't have enough time to do everything well. So that's usually. Yeah,
you have to just accept that nothing is perfect, and sometimes you just have to get something out there and done, right?
Mm-hmm. Yep, exactly. Yeah. So yeah, it's a big challenge. It's a good question. So I haven't entirely figured it out, right? So some people are just really good at it. They're really organized. Their time management.
What do you think of? Are you glad you went into computational physics?
Kind of. I love solving stuff with pen and paper, and I do that whenever I can, because it really is it really is my favorite thing, like solving equations. Rob knows this, right? We took quantum field theory, which is a really hard course together where you just crank through pages and pages of algebra and calculus. And I actually really love doing that. But I kind of went into computational astrophysics because that's where, you know, people wanted you to go, right? That's where people were getting jobs and it seemed useful as a theorist. So it really seemed like you had to do that, or it'd be very hard not to do that and get a job. But whenever I can, I try to do pen and paper. I don't know. I mean, maybe this is a controversial statement, but older people in the field who don't do computation work, they kind of look down on us younger people, relatively younger people who do computation. And they say, oh, back in the, you know, the 70s, we did everything by pen and paper, and we, you know, but they did that, of course, by doing the easiest problems, right? Doing them first, right? So it's kind of my complaint. It's like, and I apologize if there's any baby boomers on the call here, but it's like these boomers, they got there, they did the easy thing first, and then they like, you know, crap on us for doing the really hard stuff that's left yet to do. So so that's kind of, I mean, computational astrophysics is kind of the only way forward for a lot of the problems I want to study.
Gotcha.
Yeah.
Oh shoot, I had another question for you that I was gonna just slipped my mind. Does anybody else have a question? Well, I try and remember what I was gonna ask Shane.
Yeah, I have a quick one. So did you begin to become more interested in computational physics during your undergrad, or is that something you started like getting a taste for and getting a love for during grad? And if so, if it was during your undergrad, what kind of I don't know, challenges or separate fields of study outside of your normal undergrad physics studies did you pursue to try to better yourself in?
Okay, yeah, that's a good question. So I went to Carnegie Mellon in Pittsburgh, which is actually, it's kind of most famous for its computer science department. So a lot of the best people there go there to do computer science and electrical and computer engineering. Physics program's fine, but it's, you know, like my best smart friends, we're all doing this computer science stuff. And so since I was there, I actually did get close to getting a minor in computer science, but I would have had to like do a class on like operating systems or something. And I couldn't bring myself to want to do that. But I did take a lot of pretty hard computer science courses, really challenging ones as an undergraduate. In part because I wasn't sure, I wanted to hedge my bets in case I didn't go to grad school in physics. I thought having the computer background would be good, and I liked doing it. But then when I got into grad school, I didn't do really heavy computational stuff initially. And even though I did computer programming, it wasn't really like the main focus of my research in grad school. So when I got to be a postdoc, I decided to do more computational astrophysics. And I kind of had to relearn a lot of this stuff, but it was really valuable to have learned all this coding in C++ that I had as undergrad. It kind of came back to me. So that was pretty useful. And then the other thing, of course, is I took a lot of math, right? Because with physics degree, you really can't know too much math. I almost double majored in math, but I decided I liked physics more. So I stuck with the physics major. But yeah, I think that for anyone going into grad school or wants to go on to grad school or thinks they might want to go into grad school or not, like if you just want to get a job in industry, there's no one who's going to say you spent too much time learning to code or to do programming. Like a lot of faculty who are looking for research students, you want people who are proficient in coding, because honestly, those people can get up and running really quickly on research projects. And so that's a really useful skill to have.
So Shane, I had a question, and maybe I remembered it now. Do you know, like what people are doing with bachelor's degrees in physics these days, or like what do your students do for work afterwards? Do most of them go on to academics, or is the path for most people through grad school non-academic? You know what I'm saying?
Yeah, so it's interesting. Yeah, so I advise the astronomy physics. Well, I actually advise the astronomy majors, but I also talk with some of what are the astronomy physics majors. So our university has a separate astronomy program from the physics program, but a lot of our majors take a lot of physics in this astronomy physics program. So roughly speaking, I'd say about half of our graduating astronomy physics majors try to go to grad school. They at least apply to grad school. And of those, only about half get in, maybe less, because it's actually getting really competitive to get into a lot of these graduate programs. And also, you know, some people only want to go to Caltech and Harvard, and they set their sights a little too high, even though there's a lot of good programs other places. I would say if you look at the people that aren't in that group, it's kind of all over the place. There's, you know, I know a lot of students who've gone on to work at national labs in some capacity or another. They've gone to work either in aerospace engineering in some cases. We have a lot of people going into aerospace engineering. We see people going to work for companies that work for the Defense Department. So there's no shortage of people who, you know, if you you know, obviously some people don't like building weapons and stuff, but you know, some people of course are fine with that. And that's actually, there's a lot of people, you know, if you're designing missile guidance systems, you want people who know a little physics and things like that. So we have a fair amount of people going in that direction. A lot of people just going into business. You know, people with good quantitative skills are of interest to people who, you know, do financial stuff. And then of course there's this big field called data science now that's drawing a lot of people. And so there's a lot of people going into data science, which means all sorts of different things. It's kind of a buzzword, but basically what they want is they want people who can do good statistical analyses. And so you know, people who do physics degrees, particularly astronomy degrees, we emphasize learning statistics well. So, and then teaching, we have a lot of people going into teaching too. So
right on.
I would say those are the ones that are the most popular.
Cool. So let me check here. So you guys are probably getting tired and we should probably start covering some actual content. Does anybody else have one last question, or should we call it good for Shane? If you got a question, throw it out there. Otherwise we'll take our break. All right, let's give Shane a big round of applause here with the cheesy Zoom graphics. Okay. I'll give you the cheesy crying, Shane. There you go. You made me cry.
Nice of you.
I appreciate you swinging by. If I find out when Roger's coming, I'll try to give you a heads up so you can come in and punk him. All right.
I'll just sit and listen to what he has to say.
We'll make fun of him in the chat or something. All right. We'll sit in the back and text. All right. So, all right. Shane, I'll catch you later. And then class, let's go ahead and start up at say 6:08 or something, 6:09. All right. And we're going to talk about magnetic moments. Thanks, Shane. You're the man.
Take it easy.
Appreciate it. Yep.
Bye.
Okay. So again, we'll pick up there at, what did I say? 6:08 or something. All right. So take your break.
If anyone's still here, I know no, Ryan's here. I guess an example of what you could do with a bachelor's in physics. My father got a bachelor's degree in physics from Cal Poly, and he works at Vandenberg now as a systems engineer. I can't really give any details, but a lot of his work friends have bachelor's and masters and doctorates in physics, and aeronautical engineering related degrees, and a lot of them work out at military bases. Also, Ryan, what are you thinking of the vector spaces so far in calc?
It's really interesting. Hard to conceptualize at first, but so Nathan told me about, you might have heard of this YouTube channel called 3 Blue 1 Brown.
Yes. Great
So
channel.
I actually, yeah, so I looked up a video on that. Like I was having an issue with like the idea of spans and stuff like that. It was just kind of like all abstract to me. I
Yeah.
watched one of his videos on it and it just totally clicked in my head, made the homework so much easier and everything too.
Uh-huh.
Really
Yeah, I like
nice.
to,
So
I
I'd
like to think
recommend
of it like
that.
boxes. Like
Yeah,
different
exactly,
colored
yeah.
boxes, and like how does it relate?
Yeah.
Um,
So no, that was super cool. So
Yeah.
that actually really helped a lot.
Weirdly enough, what helped me was you can look online mathematical paradoxes, and one of them has to do with a set containing all possible sets. Would it contain
Oh.
itself? Yeah.
Oh
Like,
my
if you
gosh.
think about that, an infinite set containing all sets, would it contain itself?
That's insane. Yeah.
It's a
Oh my
weird
gosh.
question. Yeah,
Because it's every set.
exactly.
Goodness gracious. Yeah, no, that's interesting. Yeah, I guess in a way, yeah, as soon as you start to kind of understand some of the stuff going on, you can look up paradoxes and that might help
but
you.
then can you say it's a basis for itself? I don't know.
Oh my gosh. That's
It's very
great. Holy
confusing.
smoke.
Yeah, it's. I'll send you the paradox if I can find it later, but it
Yeah,
might
dude,
make
that'd be
sense.
awesome. Oh, that's funny.
Let me see.
There we go. Well, would you guys, I don't know how that is talking with professors instead of students. Did you guys like that or not? Or
Yeah, that was cool.
it's a little bit different, right?
Uh-huh.
I happen to know we're also ahead of schedule, so I knew it didn't matter if we go a little long. I don't know. What'd you think, Joy? Did you learn anything or no?
Yeah, I think it's always good to get different perspectives. I just thought of a question that I was going to ask him, and it's, did he
Ask
ever
Jing?
hate physics? Yeah.
Oh yeah, for sure. I remember we were sitting there working and we'd worked a 12-hour day on a Saturday, and then it's, 9 at night and we got to keep working. So yeah, we hated it. We had one class that took 40 hours a week for the homework because we had this
Okay.
teacher that chose not to teach us.
So then that begs the question, at what point can you differentiate between whether or not you're just not interested in that field anymore and whether it's just a temporary thing?
Well, I could tell you right now, it's a temporary thing because you have me. Anybody that has me is going to hate it. I guarantee. So like, yeah, because I make you guys work and I'm trying to get your technical chops up. And that's just
Right.
very uninteresting. Right? Because it's very grinding, just more. And let's face it, online is horrible. I would not make any decisions about your career based only on the online experiences that we're having because they're just terrible compared to the real world, right? Where you communicate with people in person and you talk and you think. I could tell you this too. An undergraduate degree in physics is very versatile because if you get a degree in physics, everybody thinks, oh, they must know something. And you can go from physics into anything else for grad school, right? Anything else. I guarantee it. So, I mean, obviously, like if you want to go from physics to CS, you'd probably want to have a CS minor and do some work. But when people need certain types of problems done, physicists are the solution. So there's a I'll leave it at that. I don't know.
Thank you. I like hearing that.
Yeah. I see Nick laughing. What do you think, Nick? You should have muted the screen.
Sorry. No, I was making my own jokes in my head. You were saying like physics can go into anything, and I'm just like, yeah, you can go into being like, and then I instantly thought like a midwife, just stupid things that make
You
sense.
could.
The trajectory of the baby, if it launches out this way, I know exactly where to catch.
Got it. Yeah. What were you thinking? Is Eston still in here? Where? Oh, there he is. Eston, what do you think? Did you and if you guys, Joy, if you have other questions, I guarantee my friends will answer them for you, and I'll just send the email or whatever. So if you think of something later, just say, "Hey, I had more questions to ask." All right. But Eston, what did you learn anything there?
Yeah, I liked it. I was kind of right now, personally in my life, I'm kind of, observing different niche fields in physics and trying to understand and figure out where my interests peak. And I was trying to get more out of them, passion projects as an undergrad, like what kind of stuff in that realm I can work, especially like in these COVIDian times. There's not a lot of internship opportunities, undergrad research opportunities. So my next best bet is to try to, work something on the side that I can present and be like, hey, look, I worked this out. I saw this interest and then I took the time to learn about this subject and I made this result. So that's currently what I'm trying to look for.
Well, so one thing you can do, like if you're wanting to do an independent study, you could get that on your resume by asking either Youngblood or myself, be like, I'd like to do an independent study. And now when we say independent, it's pretty darn independent, because I think the pay ends up being $38 for me to do an independent study student for a whole semester. So then what happens is I will talk to you about it and I'll be like, sure, yeah, try this, or did you think about this, or something like that. I know I've taken on a few over the years. And to be honest, right now, what can be done well is coding, right? Like you heard what Jing was saying. She's like, shift. So if there was something you wanted to play around with, we could try and get it on your transcript by saying that. And that might make it, right? That might distinguish you or something if you guys wanted to do something like that. Now, if you want to do it less formal and just work and learn something, I could play around with it too in office hours. We could talk about it or something like that. Did you have an idea about which subfield you wanted to do, Eston?
I like condensed matter right now. I like the idea of, I know there's a lot of national labs for energy, and I'm trying to look at different ways to get involved with those. So I've been emailing professors. I plan on transferring to Santa Cruz. So I've been emailing professors there who work in their condensed matter department. They've got
a long time ago, I actually applied and I was accepted to them in grad school in condensed matter, but then I went to UCSB instead. So I don't really know anybody up there. What was it? Michael Dine was the famous one, but he's probably gone now. He's probably retired. Did you hear about the room temperature superconductivity? They finally got it.
Really?
Yeah, well, they got it by crushing these materials between two diamond anvils and put them under exceedingly high pressures. Like I thought it was like 15 times atmospheric pressure, but they broke several diamond anvils in the process at 3,000 a pop. But they got it to work. Yeah, so read about the room. Yeah, which is something I never thought I would see in my lifetime. All right, we'd better actually do a physics problem. Let's this is gonna be a long class if we don't do any physics. So let's do a physics problem. I see it's time. So and I'll answer more questions afterwards, and we'll probably only have maybe one more guest speaker, but I don't know, maybe I'll try to get another one too. I know somebody that works up at Dwave. Do you guys know what Dwave is? That's the new quantum computer. He's basically the guy. So I could see if he wants to swing by. Does that maybe interest you? If so, cool. Let me know. If not, I won't bother him. Let's see. I think every student in the major needs to take the physics. Oh, right. You definitely know people earn it when they get an A in a physics class, right? For sure. All right. So, all right. Whoops. Where's me? All right. So let's go ahead and I'll bring up, let me tell you what page I want to start on. I want to basically talk about magnetic moments. So let's just, the page to kind of start is around, it was right after, what was that one? It's on page 145 in the workbook, 145. And I guess I could bring it up and do a screen share too. So let me get that up. And like I said, we're way ahead of schedule, which is unusual. So I actually have this whole week scheduled to finish with magnetic moments, and it's a one-day thing. So we'll catch up next time. That said, let me get here. All right, and screen share.
So is the goal then to finish chapter 28 by the end of this week?
Exactly. We're
Okay.
supposed to finish
Okay.
chapter 28 by the end of this week, not chapter. But I'd like to get a little bit ahead for 29 because 29 is also pretty gnarly. So we'll probably finish chapter 28 at the beginning of next class. Whoops, that's 30. There we go. We're getting close. So tonight, I'll just try and make sure you understand what a magnetic moment is. Oh, there it is. All right. So last time we ended with this problem up here where we talked about torque on a loop of wire in a magnetic field. Torque on a loop of wire. It turns out there's an easier way. So the general result that we derive in that one happens to be valid for all kinds of problems. So we're looking right here at this magnetic moment vector. Now notice this is going to get a little bit tricky, but this is the part where we're trying to understand. So if you have your book, again, that's page 145. I'm going to go to the whiteboard. So let's say we had a loop of wire like this. And I think I tried to use red all the time for magnetic moments. So let's say this has side S. It's a square loop. All right. And let's say current is flowing this way. So let me label this over here. Make that pop a little bit. Okay. And so this is the current I. Now, in this case, the area of the loop is S squared, right? The area vector of the loop is different. How do I get the direction of this loop? You guessed it, right hand rule. So what I want you to do is take your right hand, right, and curl your fingers in the direction current flows. And notice my thumb points out of the page. So this one is, whoops, that's the direction of the area vector. I'll call that area hat. Okay. So notice
It's kind of like if we were thinking about it like it was torque, right?
Yeah, a lot like that.
Yeah.
Exactly. And so all these right-hand rules have this kind of sneaky similarity. So if I say this is I hat and this is J hat, what direction is K hat? I goes to J. Always check it. K hat. I go, okay. So notice here, this is I hat. This is I, the current vector. Or sorry, not the current vector, the current. So this is current I, not I hat. Now in this case, so the area vector would be S squared in the K hat. So now what I'm saying is there's a new thing called magnetic moment. So remember, if you're not familiar with doing that's a mu here. So this is mu is N I area vector, where N is the number of coils. So you could imagine if you had a single loop of wire, N would equal 1. If it goes around 20 times, N would be 20. So it's nothing fancy there. So in this particular case, the magnetic moment is, let's say it's a single loop. So N would equal 1, I is I, and it would be IS squared K hat. All right. So that would be, whoops. This is one way to get the magnetic moment. Now, why is this a useful thing? The reason we use this is for the following two equations. Let me see if I can fit this all in here. I know that torque is equal to mu cross B external. So if I want to get torque, it's pretty easy to get the magnetic moment. It's pretty easy to get the magnetic field, and it's pretty easy to do a cross product. So now we see that there's this one tricky step of figuring out the area of the loop and then doing this right-hand rule to get the direction. And then it's actually much easier to get the torque than problem 28.13 at the top of that page. The other thing that's
I have
very
a quick
easy.
question.
Go ahead. Yeah.
Can you show again how you got the direction of the A hat?
Yeah. So I curl my fingers in the direction of current. And so for this loop, it's going, what is that, counterclockwise? And so if I curl the fingers of my hand counterclockwise, my thumb aligns with the direction. Is that what you needed?
Got it. Thank
Okay.
you.
Yep. And so the other thing that you could do with this is magnetic energy. So that's going to be, oh, whoops, that's a dot product. And I think there's a minus sign in there. I screwed up. Minus mu dot B. Even more, this equation relates to something I could try to describe to you. You already know this. Magnets try to align themselves together, right? If you get a stack of magnets and you put one of the poles the wrong way and you try and force it, it'll flip over and snap to the right direction. So what I like to remember is current loops. You can think of this as like a little bit of a magnet, right? It's a tiny little magnet, and you could think of this as being the north pole of the magnet, the thumb. So magnetic moments try to align themselves with the external magnetic field. So this is a way you could check your work on these cross products and dot products. You say, well, I know the magnet wants to align itself with the external magnetic field. So let's say, for example, B external was upwards for this particular example. So if B external is upwards, in this case, here's my, let me do it like this. Look at this. The B is the blue marker. The A area vector, or the magnetic moment vector, is this red one. And so if I could just turn it just to give you a little bit of an aspect ratio, the idea is this, I know that this red marker wants to align with that one, which tells me the torque, if this one wants to curl that way, is going to be negative I hat. Now let's see, if I plug this in, B is in the J hat, right? And area vector is in the K hat. So if you go down here to this equation and we plug that stuff in, we should confirm this. So A was in the K hat. B was in the J hat. And so K hat cross J hat, well, I know that I goes to J, goes to K, goes to I, the wheel of pain. And so K goes to J goes to negative I. And notice this makes sense. The magnetic moment wants to align itself, so it's going to try to flip up here and align itself. Whoops. It wants to align with that, so that's the tendency. Now think about this energy equation too. Energy is going to be most negative when B and mu are aligned, right? So in this case, what's the initial magnetic energy here? Well, if they're perpendicular, what's the value of a dot product?
0.
0. So this is going to start with no energy, then it wants to flip up here, and it goes to a lower energy state. So that lower energy state would be stable. So this is right. This makes sense of thinking about this as a little magnet that it's going to try to snap up here and stay there. If you try to put it the other way, that's very unstable. If you're misaligned at all, it's going to go and snap up there, or and snap up there. So, sorry, yeah. So again, if this is the external magnetic field and this is the magnetic moment vector, you know they want to come together. And if they're not perfectly aligned, this would be like trying to put two magnets with north facing this way and north facing this way. It doesn't want to do it. So if you miss it up a little bit, it's going to snap together or snap together underneath. So that's what I'd like you to think conceptually about this magnetic moment. It takes any current loop and views it as a magnet with a north pole pointing in the direction of mu. Again, any current loop is basically a magnet with its north pole pointing in the direction of mu. So let's go take a look at this and look at the same problem we did last time and try and do it with the magnetic moment. So let's take a look here on 28.14, and let's give this one a shot, okay? So you have a loop of width W, height h. H is the long axis. It's carrying current capital I. So try and write down the magnetic moment for this one. Get the torque on the loop. And so I think the B field is still, I forgot to write that down there, but the B field is B in the I hat. Okay. So sorry about that.
Could I ask you a question about that
Yeah.
B journal?
Yeah.
I was writing notes, I might have missed it, but if it depends on how the current is directed, wouldn't that change where you are on the loop?
It's the direction around the loop. So you curl your fingers around the loop. Now, let me give you a weird example that might address your question. Like maybe you're thinking about this kind of scenario right here. Is that right? Where you could imagine the current could change wildly. So it's going this way, and then it goes this way, and it goes this way. So I will address weirdo loops in a minute where it's not always in a single plane. Is that what you were kind of wondering about?
Even more basic than that, even with just the square we just drew, the current goes in a circle around it, doesn't it?
Yeah, but so if I could, let me cheat. Let me go to here because I just have some stuff written out. Where were we? We're on 163, solutions, PDFs, chapter 28. This one. And so notice I wanted to point out here, we're assuming we're talking about uniform external magnetic fields for these problems. All right. And so otherwise, yeah. And so basically we're assuming the loop is small compared to the size over which the magnetic field varies. That said, if you look right here, oh, whoops, I got to scroll down just a little bit more. The idea is, notice the two torques from the different sides end up matching up. So this is the torque from segment BC. So that's going from here to here. And this is the torque from D to A going from here to here. And so we see that the two torque segments always combine like this, right? And so if you're going, and then it's possible you could have zero torque, which is true for segments CD and I think AB. But all of these magnetic loops in a plane have this characteristic where you're going to get a torque from two of the terms, and those two torques contribute in the same direction, even though the currents go opposite directions. And that has to do with, you have to have an axis of rotation to do a torque problem to understand it. So all these torques are relative to an axis. So it makes no sense to do a torque problem if you don't know what you're calling the axis or the pivot point. So that said, relative to those, Tom, I don't know if this is helping. I think that was Tom.
Yeah, it is.
The idea is that even though the current direction is changing, we know the torque works. And so the right-hand rule is to curve your fingers around. So let's go to this one. What if I had started right here? I got to go over here. Hold on a sec. Right? If I started right here, the current would be going down, right? I still get the same thing out of the page. If I start right here, still get out of the page. Is that helping?
Yeah.
Yeah. And so, and it's this mathematical artifact that matches up to the mathematical artifacts in torque calculations. Is that good enough on that?
Yeah, thank you.
Very sneaky. Very sneaky. All right. Let's see. So let me get that one up on the screen and I'll draw it on the board again. All right. So I'm going to try and look at this one down here. So it's got B in the I hat. And we got this thing here. Whoops, this red's killing me. So this side's H, this side's W. Current flows down on the right. And then the current is I. Okay. Okay. Oh, does it look brown? My bad.
Nothing you can do about it.
Yeah. Oh, that's funny. Weird. All right. Crazy. All right. So in this case, that's supposed to be a letter H. All right. And so in this case, the magnetic moment is N-I area vector, which is, I'm going to assume the number of loops is 1. The current is just I. The area is HW, and then I got to get the direction. So for this one, I think it's into the page. Let's do a quick coordinate system. So we're all using the same. Unless otherwise specified, we usually say this is I hat, J hat, and K hat. There are times it won't be that, but usually that's what we want. Into the page, that would be negative K hat. So that would be part A. Part B. Part B of this question says determine the torque. All right. So now if I want the torque, it's just going to be mu cross B external, B external. All right. And so in this case, well, let's just plug it in. I get an I, H, W, and a negative and a K hat. Crossed with B and the I hat. All right, and so K hat cross I hat, well, I don't want to screw it up. Can you guys hear my kids just screaming like crazy out there or not?
Yeah, it's
Yeah,
great.
it's funny.
Yeah, but it's kind of cute.
Oh my gosh. Hey, girls, can you be quiet, please? I'm trying to give a lecture here. A bad lecture, but a lecture nonetheless. All right. Oh my gosh. See, all the things that I do to you are being paid back to me twofold right out there as soon as I finish. So they give it to me every day. All right, let's see what we get out of all this. B, I, H, oh, and K goes to I, goes to J. So it looks like it's in the negative J hat. And so that to me is a lot easier to get the torque than what we did in that first, than in 28.13. And that's what I wanted to focus on.
I may have missed this, but how did you get the direction for B?
Oh, I used the same B field from the 28.13. So the idea in
okay. So
yeah, I was trying to redo 28, and it's in the picture there as to the right. I just forgot to label it. That's my fault.
okay, so it was stated then.
Yeah, it should have been stated, but I forgot. It was stated in 28.13, and I just forgot to say it. So I'll put that in here. So 145. Let me make a note there. Got it. Okay. So yeah, I forgot to state it in the problem statement. Good question. Others? All right. And so just so you have another easy one to practice at home, I don't want to do all of them, but I wanted to show you one of the trickier ones. So take a look at, here's another one that I think you could do on your own. All right. And it forces you to kind of think through all the directions and make sure you're getting it right. Great. And notice it says, suppose we wish to turn on a field that will cause a torque in the K hat. So it'll make you think about that. So I'm going to leave that one for you. That said, I want to show you the one that I just alluded to with Tom when he was asking a question. Consider this one. All right. So let's say you have a class 2 zombie. Whatever, it sounded great. So we're going to assume this loop is held in place by a class 2 zombie. I know it's been a while since you had a zombie problem, so I snuck one in there. All right, and look at this crazy loop. How are you going to get the area vector of this insane looking loop? And maybe you've already looked into solutions, but hopefully not. Let's see if anybody can come up with an idea. What would you do to try and make a loop? How do you get the magnetic moment of that crazy loop? How do you get the area vector? Any thoughts, anybody?
Break it into each plane the picture rests on.
Exactly. So let's go take a look at it. And then the question becomes, well, is that going to add some extra current? Is that going to screw things up? Well, let's go look. All right, so there's the magnetic moment method. It looks really nice. So it looks like there were some parts that we didn't finish. I'll let you do that. So the idea here is you're going to take, if you have weird loops, you can actually split them up. And I wanted to focus your attention right now on this and that. Notice that when you do this, we're actually adding 2 segments, but those 2 wire segments should cancel out, right? This segment here will cancel that segment there. And so we're not actually introducing any new current by describing this original loop in this summative way. So I'll pause for a second and see, are there any questions about that? Because once you get that, the rest is easy, right? Okay. So if you have a complicated loop shape, you could do exactly what, I don't know who that was, but that was awesome, whoever suggested that. Basically split this thing up into planes and you could pull the loops apart like that. So nice job. All right, good. Let's go back and take a look at what else we have in here. Let me make this a little bit smaller. All right. Oh, so now up until this point, we were doing things where they didn't have angles. So now you could see there's going to be an angle. If you're wondering where that's going to come in, remember that the torque equation was equal to mu cross B. And so if you have a cross product, the angle matters. And so we've got to be very careful here. Let me just undo that last one. I'm going to write something down that is incorrect, and you tell me what I did wrong. Okay? So this is supposed to be in red, sorry. So it should be mu, which would have to do with the area. It should have a B. And then there should be a sine of theta.
90 minus theta.
Exactly. So don't forget, area vectors always point perpendicular to the loop. So the area vector is pointing this way. And the B field is this arrow right here. Sorry, just trying to match my drawing here. So the idea is the angle you would need is actually 90. And so this is something you've got to watch like a hawk for. Nick caught it right away. Good job. So watch out for the angles in a problem. All right, when you're doing these. And so that's fine. Now notice in this particular problem, let's read about this. This is no longer just get the magnetic moment and get the torque. This says determine the size of B. So it's a variation. And now notice it says the B field is strong enough to keep the loop from swinging downwards due to gravity. Does anybody have any ideas how you might attack this problem?
Gravity makes me think of an FBD.
Okay, sure. You could do an FBD. Let's see what else we got in the chat. Phil says net torque equals 0. And that's the 2 things you would do. You would say sum of torques equals 0. You would draw an FBD and you would get the magnetic torque. Okay, so remember, we said that was wrong. It would have to be sine of, whoops, let me fix that up. Oh, go ahead, Trey.
Maybe I'm not seeing something. Why is A pointing in the positive direction instead of the negative direction?
Because I wasn't paying attention. I just meant perpendicular to the plane. Does everybody agree I drew A vector the wrong way? Take a look at that, everybody. I screwed up.
Yeah.
All right, so let's start this one over just because then we could see. You're absolutely right. A vector should be this way. Agreed? Because if you curl your hand around that plane, the A vector points down. Thank you, Trey. Appreciate that. I was too focused on the 90 minus theta. The B external is this one. So we'd actually need to use sine of 90 plus theta, I think, right? So the torque due to the B field would be mu be sine of 90 plus? Thank you. And there's a trig identity for that. And if you didn't want to think it through, you could just be like, okay, just, yeah, that's fine. But this is good enough. So now what we also need is we need to figure out the torque due to mg. And so that's the part I was trying to focus on. You draw, where does the mass of the loop act? Or where does the weight? Say again?
In the center of the loop?
Yep, exactly. And so you'd figure this out. And then where's the axis? Hinge along the x-axis. So, okay, so let's see. Let's look here. Oh, this is a good problem. So I deliberately left the labels off and I said, correctly label the axes. And so there you got to be careful what's X, Y, and Z based on the wording of the problem. So that was part of the problem. Is just, so I think that's pretty good for now. And we're going to probably, let's call this good. What are we going to do next time? We're probably going to do 1 or 2 of these gravity problems and some torque problems. This was an old test question. And then you could see maybe there's some more magnetic forces. Yeah, this problem looks really crazy. It's not about doing the problem. It's about setting it up. So you're not supposed to do it. You're supposed to set it up. But I think that's the whole chapter. So believe it or not, we're actually ahead of schedule. And I'll pause for questions now. And